Hello everyone, I'm Ayush Nainwal from IIT Jodhpur. Today I'll present our work SoK, Zero Noise Proof Systems, an empirical and theoretical comparison of SNARKs and STARKs. The motivation behind this work was simple. Although SNARKs and STARKs are widely used in blockchain and privacy systems, choosing between them is often difficult because most existing work focuses on theory rather than the practical performance. Why zero knowledge proofs? ZK proofs allow us to prove that a computation is correct without revealing the underlying data. Today, they are becoming fundamental in blockchain identity system, layer 2 rollups, and verifiable cloud computing. As adoption increases, one practical question naturally arises. Which proof system should we actually use, ZK SNARK or ZK SNARK STARKs? The dominant systems. These two proof systems have different strengths. ZK SNARKs generate proof quickly and produce a very small proof size, making them attractive for bandwidth constrained applications. On the other hand, ZK SNARKs remove the trusted setup entirely and provide post quantum security, but they produce larger proofs. So neither is universally better. They optimize for different goals. The challenge, when we looked at existing literature, we found extensive work on cryptographic theory and security analysis. However, there was comparatively little empirical evaluation showing how these systems behave under real implementations. Our work tries to bridge this gap by providing a practical comparison that developers can use when selecting a proof system. Our evaluation framework. To do this, we implemented and benchmarked DROT 16, ZK SNARKs, and ZK STARKs. We combined theoretical analysis with implementation level benchmarking. We evaluated five important metrics: proof generation time, verification time, CPU utilization, memory usage, and proof size. This allowed us to compare both systems from a practical deployment perspective. Experimental setup. To make the comparison fair, both implementations were tested using the same Go compiler and identical software conditions. We also evaluated them across multiple hardware architectures, including Apple M1, Raspberry Pi, Ubuntu, and PowerPC. This helped us ensure that the observed trends were consistent across different platforms. Proof generation results. The first major finding was proof generation performance. Across every platform, ZK SNARKs generated proofs significantly faster. For example, on Apple M1, SNARKs were approximately 68 times faster than STARKs. This happens because SNARKs benefit from the trusted setup, which greatly reduces proving latency. Therefore, if your application generates proof frequently, ZK SNARKs are the better choice. Verification results. Verification showed the opposite trend. Our implementation found that ZK STARKs verified proofs faster across multiple platforms. Although STARKs proofs are larger, their transparent hash-based design result in faster verification in our implementation. This highlights an important point. Real-world implementation choices can significantly affect practical performance. Overall trade-offs. Putting everything together, we observe that neither proof system dominates every metric. SNARKs provide faster proof generation, extremely small proofs, but require a trusted setup. STARKs provide transparent construction, post-quantum security, faster verification in our experiments, but much larger proofs. Therefore, selecting a proof system should depend on application's requirement rather than assuming the protocol is universally superior. The decision framework. Based on these observations, we developed a practical decision framework. If an application prioritizes compact proofs or fast proof generation, SNARKs are generally more suitable. If transparency, post quantum security, or avoiding trusted setup is more important, STARKs become the preferred option. The goal is to help developers make an informed choice based on deployment requirements rather than theoretical assumptions alone. Future work. Going forward, we plan to extend the study to newer proof systems such as Halo 2, Bulletproofs, and Nova. We also plan to benchmark recursive proofs, proof aggregation, and explore hybrid designs that combine the strength of both SNARKs and STARKs. To conclude, our work provides an implementation level comparison of two of the most widely used zero knowledge proof systems. The key takeaway is simple: there is no universally best proof system. The right choice depends on the application security and scalability and the performance requirements. Thank you.